Okay, good. So our third speaker is Luis, who will be telling us about how to apply partial evaluation to reversible flowchart programs.
Yes. So hello everyone, my name is Louis, and as I mentioned, going to talk about partial evaluation of reversible flowchart programs. This work was done in collaboration with Robert Glück at the PLC section at the University of Copenhagen. So for some background information, there are two fields we concern ourselves with here. Reversible computing stems back from the 70s, and for the sake of this talk, the important concepts are the fact that a reversible program needs to be backwards deterministic, which means also that we can only work with injective functions. And also it'd be nice to be able to efficiently invert a reversible program, thereby getting the inverted program. And it has a bunch of interesting areas of application. Also, for the sake of this talk, in partial evaluation, we also concern ourselves with flowchart languages, as they are seen as very versatile and therefore foundational in some sense. However, despite both of these areas being stemming from the 70s, it's only actually very recently that work has been done on combining the two by Torben Mogensen, also from KU. So therefore, the goal of our paper was to aid in this foundation of partial evaluation of reversible programs. And by that, we have fully formalized a partial evaluator for a reversible flowchart language. We have done a complete implementation that is also publicly available on GitHub. And we have done some interesting experiments composing program inversion and partial evaluation, which we will hopefully get to later. So the plan for today is to talk about a few of the highlights. First of all, the RL language, which is what we've worked with. I will talk about some of the trials and tribulations of doing partial evaluation here in this new paradigm. We will hopefully show a result and then also talk about these experiments. So first of all, we here see an RL program. On the left-hand side, we have the textual representation, and then on the right-hand side, we then have what it would look like as a flowchart. This is the Fibonacci pair program, which is to say that we take an input n, and then we then compute the nth Fibonacci pair. The pair is, of course, needed for it to be injective. And if we were to just look at the flowchart version, this is actually kind of a loop structure where we go in from the entry, and then we n times repeat this loop where we decrease n by 1, add b to a, and then swap the two, until finally we get the Fibonacci pair. And just for the sake of it, we have the flowchart version here. I said we want this to be easily invertible. So the way you invert an RL program is by simply inverting the flow, and then thereby swapping the places where we split and where we join, which actually maybe I should elaborate on. So these diamond shapes are the traditional conditional jumps we have in programs. However, since we want to be backwards deterministic, when we join our control flow, we need what we call a come from statement, which simply is analogous to the conditional jump statement, where we have an expression, and depending on the value of that expression, we know whether we came from one side or the other. And they are, in fact, so analogous that when we invert them, we just swap them around. And by inverting the control flow, we also need to invert each step. And this is actually, I might skip a bit through this because the precise semantics are not too important. But we have reversible assignments with some expected C-like semantics, except that for the sake of injectivity, we cannot have the left-hand variable occurring on the right-hand side. For example, x minus equal x is essentially setting x to 0, certainly not injective. We have a form of pattern matching. Importantly, patterns must be linear. And finally, we have some assertions, which will become very useful later on, which also have the expected semantics of having a runtime error if we have a false value. So, traditionally, partial evaluation, we are talking about specializing a program with respect to some statically known data. And for the rest of this talk, we will be showing the static part using the color blue. And the dynamic is the unknown, the thing that will depend on the runtime program. It'll be red. Then we will do a state collection where we run through the program with this static state and obtain all the different program points. And we then specialize each block of code with respect to this static state, generating some residual code. And then we do some post-processing, such as transition compression, to make it nice and tidy. However, in the reversible setting, just doing this will cause some troubles, some of which we will go through now. For example, a reversible program requires to only have a single exit point in the same sense that a normal program would have only a single entry point because of backwards determinism. However, despite this, when we would specialize a reversible program, suddenly it might have multiple exits. This would be due to us reaching this exit state with multiple different static states. And one solution to handle this, which we took for now, was to simply make all these output variables that are changed dynamic. This is certainly a point of future work to improve. Secondly, when we do specialization, when we get to a conditional jump, we make the conservative choice of specializing both of the directions. However, when we have the come-froms here, there is no guarantee that we have specialized both of the directions that originate from it. And if we don't have both of them, then this is simply also just a syntactical issue. But we can't just remove it because we want to maintain the semantics of the original source program. Here, the assertion statement actually does the work for us. So we instead have an unconditional come-from, which then adds an assertion to the body. But perhaps the most interesting one of all is this wonderful case where, let's say, we have one source block that is specialized to multiple different residual blocks, which means that it has multiple different static states encountered. However, there is a danger if they somehow all end up with the same output state, because that means that they will all point to this same block. But we only really allow for up to 2 blocks to point to the same subsequent block with this come-from statement. And there's really no way to distinguish here where we came from. And this is actually just a massive issue with backwards determinism because, as I mentioned, this means that we all have the same static output state. Notably, this must then mean that we have performed some non-injective computation at the specialization time, which then means that we must not do that. One such issue could, for example, be if we have this simple block here, and we say that we have a static x initially and a dynamic y, and we add x to y, this is fine, but we then add y to x, thereby the current value of x now depends on the value of y, but y is dynamic, which means that the new x must be dynamic. So for example, we have the input state x is 3, y is dynamic, and the input state x is 5, y is dynamic. Both of them become the same output state, non-injective, horrible. The solution to this specific instance would then be, for example, a uniform binding time analysis, ensuring that all of the static elements only depend on other static elements. Yeah. And with that, we can actually begin talking about, once we've handled all of this and written a specializer for it, we can then begin specializing programs. Here we have a similar program to the first Fibonacci program. This is a partition program, which essentially we have an input list y's, and then we pop the first n elements of y's into another list x's. This is done in addition as another loop program. Interestingly enough, since we want to specialize here on the n, which is why it's blue, all of the forward jumps are actually static, which means that the final residual program will actually be a straight line program, and it will look kind of something like this. And then once we have this, we can do some post-processing, namely the transformations mentioned previously, and we will get, or actually, let me just say that we're specializing with n equals to 2, which means you can see that we have this loop body twice in the final residual program. And then we get this following output. This is the thing that our implementation will produce. However, I have highlighted 3 specific statements. These are some assertions. They were introduced by us wanting the well-formed come-from statements. But the annoying thing is the fact that if one carefully looks at the semantics of the program, it turns out that these are actually not needed at all. They're redundant. They will always be trivially true. But this requires some human reasoning to do for now. And here on the right-hand side would then be the truly optimal partition program with respect to n equals to 2. However, we have also done some interesting experiments. This one will take a bit of time to explain. So in our language RL, we have written a reversible Turing machine interpreter, this RTM-RL. And with that, we can take some input Turing machines, for example, the increment Turing machine here on top. And then since this is a reversible Turing machine, we can also invert it, in addition to inverting the interpreter in RL. And these 2 different choices are then the 2 different paths here on the graph. And we can do partial evaluation on both of them. And the top path is simply just the first Futamura projection. We are specializing an interpreter with respect to an input program and getting a compiled version of that program. But the bottom path, more interestingly, we are actually specializing a program with respect to the inverted interpreter and thereby getting an inverted program. This is, I believe, called the first inversion projection. And while this graph is always semantically known to be true, the interesting thing for this to be a successful application for us is actually whether the final quality of the 2 increment programs produced by these 2 different graphs, if they're roughly the same. And by that, it's a bit of hand-waving thing, barring labeling of the different blocks, but the important thing is the runtime behavior of the amount of steps executed, etc. And we did this specific case, and we found that they were actually very similar. But in general, this is incredibly tough to reason about, mainly due to it depending on not only the partial evaluator, but also the specific interpreter you have written, in addition to the inverter for that for the language you're interpreting. But we have also done some more simple tests. For example, for quantitative results, we have here a few programs. Notably, we have the reverse Turing machine interpreter that we've specialized with multiple different kinds of programs. And we see that the size of the residual programs produced is, in general, a bit bigger. This is mainly due to partial evaluation. We often unroll loops. And for example, in the encryption program, we've really unrolled a loop. But interestingly enough, for the RTM example, we actually see that the residual size is more correlated with the size of the input program you give to the interpreter. But perhaps most importantly, we want to talk about the speed of things of these same programs. We actually find that here it's especially for the Turing machines that we get a large speed up to 6.5x. If we were to talk practically for the smaller cases, this speed up could also be vastly improved by this assertion removal. We had these redundant assertions introduced. They severely harm the speed up. But in conclusion of the things we've talked about today, we have done some partial evaluation in a new paradigm. We have done the first, as to my knowledge, successful application of the inversion projection. And we have identified a lot of future work, some of which I will be continuing to work on for my master's thesis. And I think that's about it. That was surprisingly fast.
Questions?
A clarification point. This speed up was comparing which to which?
This is the speed up of the residual program compared to the original program with the same input. And we are doing speed up as in just the number of steps executed by these different programs.
So you decided that in pattern matching, the program should be linear in the pattern.
Yes.
Right? Is this a restriction that's very restrictive, right? You could, for instance, say that rather than using each variable exactly once, it could be at least once, and the program could perfectly well still be reversible. So is this a requirement that sort of, is it strictly required to require linearity to decide whether or not the program is invertible, or is there some relaxed notion of linearity or relevance?
If one wants to have multiple variables, one can still just kind of, I mean, yeah, it's like the easy way to do it. The safe way is to have them be linear, because there's a bit of like unexpected semantics of the actual pattern matching going on, because we're not actually creating or destroying any values. We're merely moving them around. But if one wants to mention it multiple times while also, promising that it's reversible, then one could simply introduce a temporary variable and then copy the value over there, and then use that in the pattern matching. Yeah.
Okay, yeah, thank you.
Other questions? So maybe it's not directly related to your work, but who is the target user of your flowchart language?
I mean, right now, this was I would like to say purely theoretical, but I would also like to think that in general, partial evaluation of just any reversible language could be supremely useful, because there are many interesting reversible languages. Of course, quantum computing, I believe, needs to be reversible.
Yeah, sure.
And also, I believe that a reversible program has a lower minimum amount of energy needed to execute compared to an irreversible one, because some energy is needed to destroy information. And then that in mind, when also combined with partial evaluation, we now further reduce the amount of computation and thereby energy needed. So I'd like to think that for the future, this work will be very useful.
Sounds good.
In the speed up that you showed for the reversible Turing machine examples, was that which path was that based on in the graph that you showed? Are you reversing the Turing machine or the program, or the Turing machine or the Turing machine interpreter?
Here we are not actually reversing anything. This is a pure application of partial evaluation.
Just out of curiosity, you mentioned there's lots of future work, and some of which we'll address in your thesis work. So, what are your plans, basically?
Well, a lot of it is also we've developed a few hunches about what is possible. For example, when we get to these wonderful issues we've had, one of them is having all output variables be dynamic if they're ever changed. This is a very annoying thing. But also, in general, this also ties in with the fact that we have a uniform binding time analysis. I believe, spoilers, that it might be possible for it to become a pointwise binding time analysis, and therefore, with a bit of extra work, we might also be able to ensure that we only make the output variables dynamic at like the last possible moment, which is at exit point, and therefore maintaining the nice efficient computation from static variables until then. We even have I had a really nice program that had a really nice speed up until we realized this issue and we implemented it, and then it just became fully dynamic now. So I'm really annoyed by it, and I'm excited to see it actually work again.
Okay, thank you. Nice.
So as a programmer, I sometimes like to validate to myself, sort of convince myself that my program is correct by writing, for instance, a little program that reduces some input to a Boolean. And but the cardinality of this codomain of my test function is very small, right? And so my unit test is maybe not reversible. Right? What are techniques for testing these reversible programs?
Yeah. So that is, of course, a very interesting thing. This injectivity can often be found to be very limiting. The way we often try to do it is we want to do things a very garbage-free way, which is we do not want to have some trace or some extra baggage along the way. But I haven't really thought of a nice way of testing these things other than just, calculating in your head and seeing the expected value and such and such. Yeah, I'm sorry.
All right, so it's maybe there will be a paper about RL unit.
Maybe, yeah.
All right.
Could you go back to the commuting diagram, please? So you said you observed that going either way, in those two paths, right?
Yes.
You got roughly approximate, did you systematically compare those two things? Now, here's the question, really. If you go through the bottom path, you basically seem to have a uniform translation, right, of the reversible Turing machine to to the reverse simulating Turing machine. That's a universal construction, and you keep the original program. And one would imagine that the top way is sort of like more refined or maybe faster, because you can use all kinds of tricks in taking the incremental, the inc version, the application program, and are not limited to whatever the universal, the generic way of doing it through the bottom. So, question is it conceivable that there might be instances of programs instead of inc RTM where you see a significant difference in the outputs, or not?
Yeah. So I actually think that this is also one of the things where this diagram is certainly only this nice theoretical commutativity in actually this case where we have the uniform binding time analysis and such, because then we maintain all of this static computation will only be done for all of it. For example, if we had the pointwise one where we do a lot of static computations and then it becomes dynamic, then in the inverse example, we will maybe immediately become dynamic and then miss out on all these nice static computations. And I think, but for this specific partial evaluator, I think even specifically the minor difference in the runtime performance we're going very down into the nitty-gritty, and it's also another thing I want to really focus on for my final thesis is the specific difference in these two programs, I believe, is actually caused by us specializing the normal program versus the reverse program, and like for the Turing machine, essentially is just looping through all of its different rules, seeing which one match. And I believe that the difference right now is caused by it looping in two different directions, and therefore the order in which they match causes a difference in the amount of instructions executed.
So the answer was yes, you expect there to be a significant difference.
Certainly. But for this partial evaluator, yeah, still, yeah, even then.
Oh, wow.
Okay, so compared to other reversible imperative programming languages like Janus, then sort of execution order can be reversed at any time. Sort of time reversible, you can press pause and rewind the program. Right? Do you lose that property in RL?
That property is in essence it's backwards determinism. In Janus, which is also the language that Torben Mogens has partially evaluated earlier, I don't actually believe that you can actually reverse it at any point. It's more the fact that you have function calls where you can decide to uncall a certain function, therefore just running it in inverse. Right now we do not have functions in RL, so you can really only do forward execution, or you can invert the program and then do complete backwards execution.
Okay, and then this procedural reversibility, is that sort of fundamentally different from the way Janus is reversible, for instance?
I do not believe that there's anything really stopping us from implementing procedures. No, RL is designed to be very extendable, I'd like to say. You can extend it with a lot of different non-reversible operators even, as long as you can't use them in like the C-like plus equals assignment thing, etc., etc. There's a bunch of future work if anyone's interested in doing cool applications for domain-specific areas.
Thank you.
Okay, so let's thank the speaker again.